The longer a telescope spends looking at a target, the more sensitive the observations become, and the deeper we can look into space. But to get the full picture of what's happening in the universe, astronomers also need observations at a range of different wavelengths, requiring different telescopes. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
The GOODS project unites the world's most advanced observatories. These include ESO's Very Large Telescope, the NASA ESA Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory, and many more, each making extremely deep observations of the distant universe across the electromagnetic spectrum. By combining their powers and observing the same piece of sky, the GOODS observatories are giving us a unique view of the formation and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Now, this is not the first time that telescopes have been used to give us extremely deep views of the cosmos. For example, the Hubble Deep Field is a very deep image of a small region of sky in the northern constellation of Ursa Major. This revealed thousands of distant galaxies, despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with GOODS, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble Deep Field in the northern sky, and one centered on a different deep target, the Chandra Deep Field South in the southern sky. The main GOODS fields are each 30 times larger than the Hubble Deep Field, and additional observations cover an area the size of the full moon.
These areas of the sky were already some of the most extensively explored, and so the combination of the existing archival data with the many new dedicated observations gives us an unprecedented view of the history of galaxies.
At ESO's Very Large Telescope on Sarah Paranal, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in near-infrared light and on the boundary between visible light and ultraviolet light. At these short wavelengths, only telescopes on exceptional sites, such as the VLT's Sarah Paranal, have a chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the GOODS regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now, Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits. Each of these was separated from the previous one by about 45 days. Now, by spreading out the observations like this, Hubble was able to watch out for new supernovae appearing over the months, providing key information for studying the expansion and acceleration of the universe due to the mysterious dark energy.
But it wasn't just Hubble making space-based observations for GOODS. NASA's Spitzer Space Telescope imaged the GOODS regions in near and mid-infrared light for 5 days at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope to capture the spectra of galaxies, spreading out their light like the colors of a rainbow. Now, the spectra allow astronomers to measure the redshifts of the galaxies and hence their distances. An extensive campaign produced redshifts for almost 3,000 galaxies in the Goods fields. Now, with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale. These projects are an excellent example of how great observatories are joining together across the electromagnetic spectrum to give us a more complete view of galaxies over the history of the universe. Already, astronomers have written over 400 papers based on these data, with even more in the pipeline. And on top of that, the observations of the Goods fields will continue in the future.